Okay, so let's start. First, a few notes. I want to start with just a quick survey so I know backgrounds. Can I get hands up if you've taken the course in algebra before? Okay, awesome. Taking topology. Cool. Okay. You know what a functor is. Cool. So I'm going to have an emphasis on examples in algebra, so this works out. When it comes to pedagogy, please ask questions. I don't believe in stupid questions. I either like questions about clarification, questions about like extensions to what I'm doing. Please do feel free to ask. If I think a question is not appropriate, I will just use an answer. That's fine. I also will definitely make mistakes and forget things. Yeah, please do point those out. Generally my approach, there will be many times where I'm asking for like the class to complete definitions and such, so please do contribute. Sometimes it will be hard and you will get it wrong, but that's okay. This part of the goal is to sort of workshop definitions until they are what they have to be. Does anyone happen to have colored chalk? Okay. Figured not. Oh, hello. Welcome. So, cool. So there's good news and bad news. The bad news is that I was like supposed to prepare for this, and instead I spent 5 hours trying to understand the Donetta lemma. The good news is that now I understand the Donetta lemma. So when we get there, I'll be able to tell you about it. But that means that this will basically all be off the noggin. I'm going to do some bastardized combination of me talking and a presentation that I made for like my algebra seminar. So that will exist over there in theory, and I will be using that here and there. And I will not be doing quiver representations today. So largely the plan today. Also, this is recorded. There's my phone. Any questions before I begin? Cool. So I'm nervous. We're going to do this. This will be fun. So I'm going to start by defining what a category is. And my definition of a category is going to be a bit different from the one that you saw in class. There are a lot of different ways to define it that are all end up being equivalent. In my case, I have my set of objects, and I think set, but you know, it's a collection of objects. There could be set theoretic problems. I'm going to keep saying set this entire lecture because I don't care about set theory. So the set of objects, and for every pair of objects, a set of morphisms. So I know in class generally, if I remember correctly, the approach you guys took was it was like a single large set of morphisms. I prefer it this way personally. It means that I can just say that whenever I have one in morphisms from x to y and one morphism from y to z, they compose. And I don't need to have like domain and codomain functions that I have to check on every morphism before I compose things. I will call these many things. This is my set of objects, sure, but this is arrows, morphisms, homomorphisms, whatever is most relevant in the given category. So anyway, my categories have objects and morphisms. The morphisms compose when they're compatible. This is what it means for morphisms to be compatible. There exists an identity morphism for every object. And composition is associative. So, you know, but whether or not, okay, actually, we'll start with some examples. This is not a category. Why is it not a category? Any takers?
No A2C.
No what?
A2C, no.
Yes. So F composed with a G does not exist in this category. Now it does. Still not a category though. Why? Yeah?
No identities.
Exactly. So now we have a category. Now, we're always going to have identities. So when I write a category, from now on, I'm just going to not draw the identities because it's a lot of work to draw them every time. But you just have to know that they're there. This G inverse thing is shorthand for these two relations, right? This is just a separate morphism. I've just named it G inverse. And what that means is that when I compose it, I get the appropriate identity, depending on which side I compose it on. So because there exists a pair of inverse morphisms between B and C, we say that B and C are isomorphic in the category here. Also, in this particular example, all paths between a given object pair are equal. Right? To get from A to B, I can go down F, or I can go down like G O F and then G inverse. Right? And those are equal because composition is associative, so that's G inverse of G O F, and that's F. This is not always true. We can have non-commutative diagrams. Here's a very simple example of a non-commutative diagram. Here is the integers. Here is the integers. This is actually this is the real numbers. These are abelian groups. This is the times 1, and this is times 2. This is very clearly not a commutative diagram. Okay. Commutative diagrams will be important, but it is very easy to accidentally assume that all diagrams are commutative. They are not. Okay. So, whether or not you've seen categories before, which you seem to all have, you should be familiar with at least some of these examples. So, in all of these examples, we have objects, sets, topological spaces, vector spaces, and some the distinguished type of function between them. And this is generally what you do whenever you do something in algebra or topology. You have your type of objects and you distinguish, okay, I care about continuous functions only between my topological spaces, or I care about field homomorphisms or whatever. And this is like kind of the most common type of category that you'll encounter in the wild, because function composition is associative kind of by definition. Right? But not all categories are like this. For example, the natural numbers with less than or equal. This can be any partially ordered set, but I'm sticking with the natural numbers for now. In this case, we have a unique morphism from x to y if and only if x is less than or equal to y. The axioms of a partially ordered set mean that this is associative and identity morphisms exist because this is less than or equal. So like if I just had less than, this would not be a category. We also can have some more, wonky categories. Category of data types, where the morphisms between them are computer programs without side effects, which halt. Like, I can have morphisms between them. I can compose computer programs. I run one after the other. I start with something in some data type. I end with something in a different data type. Category of cat. This is the family tree, right? Like, you can do whatever you like here. So, I'm going to do another example of categories. But again, please do interrupt me with questions at any point. Now is a good point, for example. Oh, I totally forgot to mention something. It's the trivial thing. So, like, after, this is sort of a sidebar, but after like 5 hours of staring at the net lemma to understand it, I finally concluded that it's trivial, right? Now, like, this is a meaningful statement, okay? Trivial does not mean obvious. Like, trivial means something very specific in math. A trivial statement is something that's true by definition. So like 5 is the only prime divisible by 5, that is trivial. 45 is divisible by 5 is not trivial, because you have to go out and divide 45 by 5 and check that there's no remainder, right? A trivial problem is only as hard as like the concept. So find the roots of this already factored polynomial is trivial. Find the roots of this non-factored polynomial is not trivial, even though they're the same polynomial. Right? Okay. So the Unetta lemma is trivial. It is a direct consequence of the definition. There's no like difficult like algebra that you have to do to get there. It's just true. And you'll see a lot of things in category theory classes trivial because they are. That doesn't mean necessarily that they're obvious. That is by the fact that it took me 5 hours to understand the Unetta lemma. So I just want to get that out of the way. Okay.
Sorry.
Yeah.
The natural numbers example, can that be generalized to any postage?
Yes.
Okay.
Good. So, okay. Before I do my example, I want to talk about some ways to construct categories from other categories. So, given some category, here's some category. We can make the opposite category COP, where the objects are the same. Okay, either running obj C, I'm tired of that. Obj C is going to be written as C naught. Okay, you're going to have to deal with that. Morphisms, C1, I will write. C1 of like X. C1, C-op, so the morphisms in C-op from X to Y are the morphisms in C from Y to X. So, for example, make sense? Okay. One way to build categories. Another one is product of categories. So if I have C and D, so the product category, C times D, has the object set is the product of the object sets of C and D. So the objects here are pairs of objects in C and D. And then the morphisms between, we'll call this, say like, from XA to YB, right? Because we have our objects are pairs in here. So X is in C and A is in D, so on. Man, this eraser is so bad. Is equal to C1 Y times D1 of A. So our morphisms are pairs of morphisms, and our objects are pairs of objects. Straightforward? Okay. So this, I'm going to call it, for now, I'm going to call it N. Okay. So like N times N is the natural numbers times the natural numbers under the partial order given by your down and left in the class. Okay. Cool. Question on this? Okay. Now I'm going to do a more interesting example. So, I would like to build a category of paths between points in the topological space. So, I would like my category of paths in X. X is my topological space. I shall call it M. Maybe it's a manifold. So, paths in M. Okay. So, the objects of this are going to be points in M. And the morphisms, this is the first draft, are going to be paths between. So morphisms need to be able to be composed. How are we going to do that? Well, there's kind of a most immediate answer. So let's say path between points is not very specific. So let's be more specific, right? So let's say continuous functions from the unit interval to space, right? So where 0 goes to the point, where 1 goes to the point, and it's path. Okay. So how do we compose? We might say f of g is f of over 2 for t, sorry, f of 2t for t less than half, and g of 2t minus 1 for t of that. Okay? So, sorry, it should be g. Oh. Yes? So, if I have some path here and another path here, I compose them. Now I'm going along this path twice as fast, along this path twice as fast. Now I have a new path from here to here. What do you guys think of this category? Is this a valid category? Well, we have axioms, identity, associativity, and the ability to compose. We know we can compose, we already decided how, right? This like requires that f and that the end of f is the start of the g, but that's already implicit in our definition. Okay. Identities exist; it's just the constant path. Point. We need associativity. Now we have a problem here, because so let's sort of grid this up according to the time that we've taken the long path. So the original path here, let's break it up into orders. Okay, so like 1, 2, okay. Now when we compose these two, we get this, right? Because we're going along this path twice as fast. If I take a third path now, and I compose it, and you, okay, like it's a deal of the same point, okay? So, okay, now, this is my position, right? If this is like F, G, H. This is G, O, F, H with 4 lines. Okay. If I do it the other way, I will get bad drawing, whatever. You get the idea. Like this. So here I'm going very quickly along here, and then I spend half the time here. Here I'm spending half the time here, and then I go very quickly along here. These are different functions from the unit interval at the end. So, as written, this is not a category, because associativity doesn't work. We can resolve this by allowing up to continuous reparameterization. So that's pre-composition by some function from 0 to 0, 1. And that will resolve this. And the morally correct thing to do is to check that and to actually write down what is the thing that you have to precompose with 0, 0, 1 to get this to be equal to that. Now we have a category. Questions about this? Okay. I will note for those of you who have seen some topology and some homotopy stuff is if instead of just allowing reparameterization of the input, we allow arbitrary continuous deformations of the function, then this is now paths up to homotopy. And the category that we've created is called the fundamental groupoid of the space. Fundamental group is, you start and end at the same point. Right? Here, we don't necessarily have to start and end at the same point. Cool. It's called a groupoid because every morphism has an inverse. That's what that word groupoid means. Questions on this? Okay. We're gonna move on to functors next. No, we're not. We're gonna do products. Okay. Forgot about that. Okay. So let's do products. I'm gonna send that away for now. Whoa. Bye. Okay. So, product. Owl is, I think so, go?
Yes.
Great. So, we would like to define an appropriate definition of product in an arbitrary category. To do this, we're going to take inspiration from sets. So, let's consider the latest set for a minute. Okay? I have two sets. They call the sets 1, 2, 3. Let's call this set S. And I'm going to have T, the set A. Okay? 1, 2, 3, A, and B are all sets also. Okay? Here is a definition if you want one. It doesn't matter. They are just sets. So, I would like to define the product of F and T. How do I do this in set? What is the product of F and T? Anyone? No. No one knows how to take that product? Come on, you can do it, guys. F times T as a set.
1A.
Yeah, 1A. Great, thank you. Okay. 1A, 2A, 3A, and 1B, 2B, 3. Okay. This is a good first pass. Now, these are all sets, right? Okay. What is parentheses 1 comma A? I don't know what parentheses are. Okay. We want to define ordered pairs here, right? But like, we're sitting here in set. We have to find a way to do that in set. Does anyone by chance know how to do that in set? Yeah, you want to? Okay. What is 1A as a set?
I think the standard construction is like a set of 1 and then the singleton A, right?
The set of 1 and singleton A, you say?
Right. It's been a long time.
It's possible that this works. I have no idea. Right? There are many ways to do this. Another way that you could do it is you could have the set of 1 and the set of 1 comma A. Or you could even reverse that, right? You could have like A and then the set of 1 comma A. What makes one of these better than the other?
Well, in the second and third ones, one is a subset of the other.
True. Okay. So there's some nice property that you might want out of the ordered pair. But does that make the ordered pair defined based on that a better product? Like, you know, let's call this like, I don't know, like 1A protrusion. And let's call this, like this one like 1A left. And then this one is like 1A right. Okay. Like, you know, I could, you know, do like the product with the protrusion ordered pair or with the left ordered pair. I don't really see any reason to prefer one over the other. In fact, it doesn't really matter which I choose because these are all isomorphic. There's this nice little thing about sets, which is any two sets with the same size are isomorphic. Why? Because there's the bijection, right? So, like, these are all isomorphic. Like, all these products have 6 things, so they're isomorphic, right? What else has 6 things? Like, that has 6 things. That's isomorphic to this set, right? But if you ask me, this isn't a great product. Why? Actually, before you answer that, let me do something that I think is a slightly better product, but still not a great product. what works here and also here that doesn't work up there? This is not an easy question. I'm gonna wait a minute, see if anyone has an answer, and if not, I'll tell you the answer.
Are you treating these as just symbols?
These are just, I mean, like,
Symbols that we can read.
exactly. They are symbols that you can read. That's actually an important detail. And we want to formalize that. Like, you know, like, fundamentally, like, 2B means nothing, it's just a symbol. Right? F means nothing, it's just a symbol. We can't distinguish these things. These sets are isomorphic. So what do we need to make it a good product?
I enjoy being able to flatten things.
Okay, great. Elaborate. You have the right idea, you just have to put it in words that the rest of the class understand.
Can't remember. I can't remember the words. You enjoy being able to like create a map that gives you enjoy being able to find a map that like gives you the original sets. Actually, that seems to be a nice thing to have.
Exactly. So let's call this like S. This is like concatenation product. Okay. And let's call this the like number. Okay. So here I can pull that out, the A's and the ones, right?
So like projections.
What?
Projections.
Exactly. We want projections back down onto F and T. I need a function. I need pi s from f cross t to s, and pi t from s cross t to t. That can tell me like what are the two parts of my ordered pair. That's what we care about with the ordered pair. Is that there are two things in it, right? And I can distinguish them and I can pull them back out. So really the actual set that is the product doesn't really matter that much. What matters is these projections. These are the fundamental thing about the product. And so I know how to define projections here, right? Like I can define projections where I can say that like, you know, like where like 1A maps to 1 and to A, right? 1B maps to 1 and to B. And if I define projections through up here, if I say A maps to 1 comma A, B maps to 1 comma B, C maps to 2 comma A, D maps to 2 comma B, and so on, this is just as fine a product as this is. Right? So we care about isomorphism, right? Between the sets. And the isomorphism critically has to preserve these projection maps. Right? Questions on this? Okay, great. So, now, let me give you another candidate product. Okay? So, S times T star is going to equal, we'll do like S times T union star. What do you think of this product? I don't really have projections down to S and T like implicitly, but I can just make one. I can just decide that this goes to like 1A or whatever. Like not super interesting. Or, you know, to be sort of more general, maybe I can even do times like, and I can just ignore this, I guess, right? Like, I can even just ignore the PQ component. I can just decide that like 1AP goes to 1A and 1AQ also goes to 1A. What makes these worse than the other guys? Maybe. This is a much harder question than the other one. And you know, there are a few ways to answer this one. But one of the sort of more heuristic ways to answer it is there's more information here than you need. like, I don't really care about the P and Q. I sort of added more structure that was unnecessary to begin with. This ends up not being isomorphic to this, right? Because this has twice the size of that. Like, in fact, there are multiple ways for me to define a projection map down on this guy that are compatible with everything. But things are more unique here. There's like very clearly one way to do it. So that's an important reason to prefer this guy. Let's do another bad product. S cross T. I'm going to define this to be S. Okay, where I'm going to, my projection map to T is just going to take everything to A. Why is this a bad product?
Very lossy.
Very lossy. Let's be more precise about that. How do we quantify the idea that we've lost information about T?
Well, we don't really have a good projection to T, but I guess
Good.
in some cases
it
it might so happen that we have, you could define a map from S to T, but that doesn't feel intuitively like what we want to project to T.
Okay, so I've been writing these like this. This is like this. What I've been writing is not enough to define a product, right? I have to write down pi s and pi t, right? So let me do that. I'll say like pi s, pi s. This is s product, right? Okay. Pi s of I'll do h for half. Okay, this is half of thing. So pi h s of like like s and s is s, right? Okay. Pi t h of 1 is a, of 2 is b, and of 3 is b. Okay. So my pi t still does cover all of t, right? Like intuitively, this is still a bad product, though, right? You're right that it's still lossy. It's lossy in a very particular way. The way that it's lossy is that we can't, like, when we think about a product, how do we get an element of a product? We choose a thing from S and we choose a thing from T. So we might imagine that we have some object, call it P, that has a map into S and a map into T. That's what you call this thing X. Okay? This is what I'm using to pick a thing in my product. Right? And to make the product work, so let's say that the product is here. The product has my maps pi t and pi s onto S and T. For the product to be valid, I need to be able to reproduce these two selections of S and T by going through P. There has to exist a map here. So, as an example, if I take X to be that, and I take these two arrows to be the pi for this guy, is there a map into, S times HT into this set, which reproduces pi S and pi T? There is. Right, because we only get 3 things out of here, right? Like this is not gonna work. You can try and it won't work. We can write down a map, for example, which takes 1A to 1, 1B to 1, 1B to 1, but now that means that if I look at that map at 1B, it ends up at 1 here, which then ends up at A in T. Right. So I'm not able to actually recover what I wanted to recover, which is B. So the existence criterion of this map into P, which calls this diagram to commute, which we usually write like this. Like we just draw some little circles. The existence criterion prevents things from being lossy. Now, if we think about this guy, if we try to use this as our product, and considered maps from S cross CT into here to reproduce these two arrows, there would be multiple different ways to get from here to here, but that we reproduce the projections that we want. We could either send things to things ending in P or things ending in Q. That's because we have this extra structure. To prevent the existence of that extra structure, we can demand that there exists a unique map from X to P. This criterion is the definition of a product. You have two objects, S and T, or more if you like, and for all objects X that map into S and T, there exists a unique map from X to your product, such that composing with the projections reproduces those original maps. Questions? Yeah.
What is this? So at the moment, are these all sets?
Yes, right now they are all sets.
Okay. Why would X to P be unique in the sense of reordering what gets mapped to what?
Great question. And the answer has to do with pi s and pi t. So let's take an example here. Okay, let's call these like F, S, and F, T. Okay. So let's take an example. I'm going to erase these. Let's see. Let's take some set X. Let's call it that. Okay. This top guy. Okay. So S. This is my X.
My question was about when they're the same size, but
When they're the same size.
yeah.
This answer should answer that, I hope.
Okay.
Yeah. So we have this like S times P Q T is going to be X, and we're going to let P be I don't care, any of the good products, right? We can do this guy, okay? The concatenated product, okay? So we have pi s and pi t as part of the definition of the product, right? So pi s equals, so like pi s of like 2b equals 2, pi t of 2b, b, etc. Right? Yeah. So if we define, like our fs of like 2ap equals, 2ft of 2ap equals a, etc. There is a unique map into P, which reproduces these functions, because 2AP has to map to 2A. It can't map to anything else, because if it mapped to something else, we wouldn't get the correct thing. Okay, let me stick with B just for consistency's sake, right? 2BP has to map to 2P, because if it mapped to anything else, we wouldn't reproduce the 2 and the B that we want over here. Does that answer your question? Awesome. Other questions? Okay. So, this is now our definition of a product in set. But notice, I never said anything about sets in this definition. I only said things about morphisms, right? And the existence of morphisms and the uniqueness involved as well. Okay? This is the definition of a product in general in any category. So we can take an example. We can take, let's say, like S1 times the unit interval. Okay, I'm gonna call it I. Okay, so the product is a cylinder. That's not enough information. I need the cylinder, and I need projection maps onto S1 and I. Right? These will be taking the height and taking where I am around base circumference. Now, there are a variety of different cylinders and different projection maps, but they're all isomorphic, right? As long as things are unique, there exists a unique guide out. Let's see. Can I do something clever? What's my list of? I'm gonna think and see if there's something clever that I can do with one of the more obscure categories. So products don't always exist in any given category. For example, I'm not convinced that there exists products in this category. Because I don't know. Let's do the equivalent of that definition. So I have 2 points, right? And I want the product of them, which is the third point, and projection map, aka path, right? Such that for all other points, there exists a unique, for all other points which have paths to here and here, there exists a unique path to here which reproduces those 2 paths. But this path is not the same as this path, right? So products don't exist here. Let's do something a little bit different. We can look at my good old friend N over there. So take the number 2 and the number 4. And there exists morphisms down, right? There exists a unique morphism from any larger number to any smaller number. I think that's how I defined it. I may have wrote this. No, I got chalk on my fingers like this.
But you should ask.
Yeah, did that from your question? Please do.
Wait, go, repeat the point example.
Yeah, okay. So, what is the condition for a product? So, I have 2 points, S and T. And I'm pretending I have a product. Okay. And projection maps, phi f.
Projection maps in this case are
Their path, because all of this is their path. Such that for all other points x and paths f, f, and ft, there exists a morphism.
there's a unique path between x and t,
Yeah.
and that's why that's not okay.
And the issue here isn't even uniqueness, it's existence. There doesn't exist any path from x to p such that this composite equals this, right?
Unless
How do you go
unless the f's are already defined to go through t.
Exactly. In that case, there might exist a product. So uniqueness is still a problem. But some products do exist in this.
You could
Oh, no, there is a product. There is a product. No. There is not a product. My bad. I was for switching my quantifiers. Yeah, so I can always just pick a different x, right? Like, the point is here that the product given has to work for all x, and that's not.
For all x. And for all, wait, how are the f's chosen? As
For all x's with an f and an f.
Okay, for any f.
Yeah.
Okay.
The product has to satisfy this. So in the set example, right, for any other set that has maps to S and T,
For any other.
I can factor it through P.
It's like you're condensing.
There is a unique way to
Yeah.
decide how to name each element its x.
Does this make sense? Okay. I want to try natural numbers. I forget if I define things that, like, there's a morphism going down or going up, so we're just going to stick with going down for now. So I want a product of 2 and 4. Right? Like, notably, my category looks like where, like, I have arrows like this, and arrows like this, and arrows like this, and arrows like this, and so on, right? Okay. This is my category. And also identity morphisms, so I'm not going to draw those because, oh my god. And I want the product of 2 and 4. Or let's say like 1 and 3, okay? Sorry, 2 and 3, let's say. I want the product of 2 and 3. Which I want to be an object such that for any other like object which has morphisms down into 2 and 3, those morphisms factor through my product, right? In that case, 3 is a valid product. Okay, 2 times 3 equals 3, famously. Where my like projection map onto 3 is identity, and my projection map onto 2 is just the unique map from 3 to 2. Because any other, like, because this entire category commutes, right? Any map from, say, like 5 to 2 is a composite of the 5 to 3 map with a 3 to 2 map. So, 2 times 3 is 3. Good. I found the clever thing I was looking for. Questions on products? Okay. I will now proceed. I'm going to erase this. You guys understand product category. It is the product of the category. Great.
Out of curiosity,
Hmm?
does the manifold points example, like, does that work if you like go up to homotopy or something?
Great question. Don't know the answer.
Cool.
If I thought about it, I might be able to tell you. Does that work? Are you referring to the product?
Yeah, like, can you define the product if your paths, your equivalent is up to homotopy?
I think so. I think not all. I think if your space is simply connected. Sorry, if your space is connected. Wait, maybe you can just always define it. Do people here know what homotopy is? Not everyone here knows what homotopy is. Okay, so I'm going to define what homotopy is very vaguely. So if I have some path from 2 points, I'm going to fix the endpoints and I'm going to jiggle the path around. So I can sort of like wiggle it like that. Okay? This is a valid homotopy. A homotopy is just a continuous deformation of the path itself, where I fix the endpoints. Okay? So, like, this path is like this path equals this path up to homotopy. Right?
You're talking homotopy without the endpoint string.
Yes. But if I have some like hole in the board here, right? This path does not equal this path up to homotopy. because I can't wiggle this to get that. Okay. So, the question is, given any 2 points, because they're always equal to the product. So, if the space is simply connected, I think the answer is yes. Right? Because I think that you can just, like, you can just wiggle this path to this path, right? And then you're chilling.
It occurs to me that even if it doesn't, even if not, like if you have your points, if you have your path like x to s, x to t, then there is a path from s to t by definition. So
Oh,
you
true.
can kind of just.
Wait, no, but I actually, I think you're maybe screwed because the oh no, yeah, you're not screwed. Yeah. I think you could just be correct here. Like, yeah, because even if I have okay, no, but the product fixes pi f and pi t. Like, the product has pi f and pi t bundled with it, right? So let's take this example, and let's say that these are s and t, right? And I have, like, I want to define some product. Let's say that my like product is over here, okay? Like, right? This is like pi t and pi x. Now I have some guy x over here with these two, like, ft and fx. Is there a path from, yeah, I guess I can just go down t and down here and then decompose, right?
Yeah, I feel like the question this is resolving to is like what happens to your product definition when like there are no possible x's that have maps to both s and t.
Then it's vacuously true.
And it's accuracy true, so it works.
Yeah, I think you're right that it works. Because in case you missed the trick here, the composite, the oh, wait, no, I don't think it works though. Because you need to pick one map from x to p, which gets both ft and fs. And so let's say that I pick, like, upper ones will be like this map, right? Okay. Well, it gives me, like, this composed with pi t is equal to ft up to p. But this composed with pi f is different from fs.
Okay.
So no, it does not work. This is not a valid product.
Okay, cool.
I'm not convinced there exists a valid product in a non-simply connected space. But if it is simply connected, I think it does work if you're up to p. Cool. Interesting question, thank you.
So I'm back to thinking about the Vegas case. Like, the Vegas case, do you need like so if there's no such, so there have to so
Oh yeah, you do need there to be a p to begin with. There do have to be like maps to s and t. So if I have like two disconnected regions and I have like s over here and t over here, there's no product because I can't have any point that has a pi f and a pi t. Regardless of the x thing, the pi f and pi t just need to exist to begin with.
Yeah, okay.
Good catch, thank you. Cool. Next, we're going to talk about duality. No, we're going to talk about coproduct, and then we're going to talk about duality. Is that what I want to do? I think so. Yes. Okay. So, coproducts, also known as direct sum, but I'm going to say coproducts for reasons that will become clear soon. Okay. So, oh wait, I kind of want to do a vector space example before I move on to coproduct. Do people here would know what a tensor product of vector spaces is? Hands up if you know what a tensor product of vector spaces is. Okay, so not everybody. Okay, so I'll do the vector space example with the coproduct. We'll do coproduct now. Off the noggin, guys. Come on, I'm trying my best. Okay, so we want to define a direct sum. Okay, so I'm going to call it coproduct, or a disjoint union, or whatever. So I have my S and T from before. We are in set again to begin with. I have S and T from before. What is the disjoint union of S and T? Anybody? Come on, guys.
Zero S times 1T is it elements?
0S.
Sure.
Order pair 0S times order pair 1T.
Yeah,
Or-
Not times, usually.
Yeah, I do.
Sure, why zero is?
Oh, you're saying like this, like 0.2, 0.3,
It's really one thing.
1.8. Yeah, that's more sophisticated than what I was thinking. I was just thinking 1, 2, 3, ABC, ABC.
Yeah, I had the second picture in my head for like the last K years, and then like I searched up disjoint union on Wikipedia like a couple weeks ago.
Yeah, you're like objectively correct because like what if S and T have some of the same things in them, okay? But like before, the definition doesn't really matter,
Yeah,
right?
yeah.
Because these are isomorphic,
Of
right?
course.
We don't care about the object, we care about the morphisms, as is usually the case in category theory, right? So what are the morphisms that we need? What are the defining properties of a disjoint union? Yeah.
Well, if you have an element in S, then there should be corresponding element in S union T, or disjoint union T, right? And similarly for T.
Great. I'm not sure write this differently.
And in the set case,
What
the
is
useful
the-
property would also be like, these two images should ideally be disjoint. But
Yeah,
category.
true. Okay. Okay, we're gonna be over here. We have S and T, and they both have maps into S.
Yeah.
Okay, I'm gonna say it's Boston. Okay, so before any element of S times T gave us an element in S and an element in T. Now, an element in S gives us a thing in S plus T. Now, an element in T gives us a thing in S plus T. Okay. We can, again, define things by means of a universal property. Because, like, we care about consistency conditions. Right? What are the consistency conditions that we care about? We want things to be not lossy, right? And we want things to be, like, optimal, right? Okay, so, like, we want exactly enough structure to make this work. What does it mean to make this work? It means we don't lose information. How do we say that? It means that if we have any other object X, and we have maps from S to X, or T to X, there exists a unique map from S plus T to X. Like, for example, you could let this be X, and let this be the identity map, and this uniqueness, this property guarantees then that you haven't lost anything in S. You haven't lost anything in T. Right? So, does it make sense? Yeah, question.
Is the product or co-product exists between, all the pairs of elements? You have 3 objects in a category. Is the product operation necessarily going to be associative?
Great
to
question.
isomorphism?
Fantastic question. The answer is yes. It's a great question. There do exist canonical isomorphisms between like S cross T cross U and S cross T cross U. These isomorphisms do exist, and you can prove that using the universal property. It's like this then expands out into you have like like say like this is now like t times u, which now has additional arrows, right, into u and t, and like you still have your x and like et cetera, et cetera, et cetera, right?
You iterate the construction similar to how the universal property can be used to show that P itself is unique. Or
Yeah.
sorry, yeah, up to S one.
Yes, yes. Like in particular, take P and P prime. There exists a morphism from P prime to P and from P to P prime, therefore they are isomorphic. Yes. Oh, and decompose to the identity. Why? Because you can choose the morphisms to be the identity. Okay. Cool. Yes, this is very important. And the fact that this is true means that you can then define a product of three things. Right? You can just have like S, T, and U, and have your single P, which maps to all three of them. We're gonna get to that soon. I will come back, I promise.
Yeah, I assume that we can do that for like, you know, an infinite product over
I will
an
come back.
arbitrary subcollection. Okay.
Yeah.
Just notationally, we've defined the categorical product earlier. We've defined this product.
What is this product?
Like, or wait, am I stupid? Never mind.
What? No, you're not stupid. What is the question?
Wait, sorry, no, we defined the product category earlier.
Yes.
Yeah.
The product category is different from a
Yeah.
product in a category. Yes.
Yeah, are we, okay, right, to be clear, here we're multiplying on elements, there we're multiplying on categories.
Exactly.
And just making sure we're distinguishing things notationally.
Yes. Thank you. Great question. Later we will see that these are, that we aren't, later we will see that the reason that we aren't distinguishing them notationally is that they are the same thing as in different categories.
Okay, fair enough.
Like the product of categories is a product in a category of categories.
Cool.
Great. So, here we are. So, we have the definition of a disjoint union, which is that, like, S and T are in it, and nothing else is in it. Right? Cool. Questions? More questions on this? Yeah. Is that a
I
question?
guess
or-
could we look at an example of like
Yeah.
something is a product?
Yeah, this is the co-product. Sorry, let's call these like, I don't want pi anymore. What's the canonical I? It's an inclusion. It's an iota. Okay. Iota S and iota T. Okay. So like iota S of 1 equals 1, etc. Right? Like iota T of V equals V. So like, you know, I could like name these something different. I didn't have, right? And now like, great. And if I have some other thing that I want to map into, so like, let's say that like S and T both map to, what's something fun that these can both map to? What? Let's say that they both map to R, okay? So like, let's say like Fs, we'll call it G now. It's like GS of S equals S, remember? And GT of A is GT minus GT of B equals 5. Okay? Cool. So now we have two maps into R, and there does in fact exist a unique map from S plus T to R. It maps this to 1, this to 2, this to 3, this to 5, this to 5. Pick up? Great. Okay. Other questions on Coco? Oh, also this diagram can be important. Also, like, usually when people write down these universal properties, they like have them, they draw this like arrow like dotted, which I would do if we're not like Crayola. The point being that like you are like we have S plus T. Given this guy with G, S, and G, T, the property said that there exists a unique map here. Okay. Cool? Good? Okay. So, let me point something out. Look at this diagram. Look at this diagram. What do you notice? Connection between these two diagrams. What do you notice? Come on, this is an easy one, guys.
The arrows are flipped.
Wow, the arrows are flipped. Thank you, Kai. So, the arrows are flipped. This is the dual of that. Dual means you flip all the arrows. When we have a dual thing in category theory, we put co in front of it. So, this is a and if it, yeah, the dual of the dual is just the original, right? So I took this, like, there's the crash course, which is the weak class, and I made it a co-crash urse. Okay? So that's what happened here. So the arrows are flipped. The vast majority of things in category theory have a dual construct. And like, not necessarily in the same category, right? Because maybe there exist like products, but not co-products in a given category. Like in set, all products and co-products exist if you believe in the exact of choice. Like, I'm pretty sure that's wrong. But like, there are categories like our path category where not necessarily exists, where like this is not necessarily true. I'm actually curious if co-products exist now. I'm going to spend about 1 minute staring at it to see if I can figure that out real quick, and if not, I won't waste any time on it. So SUT go to 2, I don't want not 2, and I this come up here. I think it breaks for the same reason as before, right? Because these are like the directions high key do not matter.
Yeah.
Okay. Cool.
Pseudo science.
So if I have a co-product, this is a product in the opposite category. Because the arrows are all flipped. But cool. So let me do another. Okay, so I'm for now done with co-products. Oh no, I'll do an example in a different category. Right? I'll do an example in vector space. So I'll do both the co-product and a product example. And those who don't intend the products will just be sad. No, I'm sorry, I can't do anything about that. So if it's two vector spaces, V and W, right? Okay, so V is gonna look like R3, and W is gonna look like R2. Okay? So I have some other vector space. So I want to find let's start with the co-product. Okay. This is a vector space where by the map out of V and a map out of W, they can be factored through the co-product. Right? So like our intuition from before was like V and W are both in it, like just separately. Any guesses for what this should look like? The co-product.
Sorry, R5.
Yeah. So this is going to be isomorphic to R5. And this is not enough information. We also need the map where there exists these like iota W and iota V. Right? We need to, because like we can't just say R5, we also need to decide which part of the R5 is W and which part of the R5 is V. So like, for example, we might choose the first 3 coordinates to be V and the next 2 to be W. And I hope it's clear how this property holds for any other vector space. That's all to see. So, now let's find the coproduct. So we want V times W. What does this need to satisfy? Any vector space that maps.
Or you mean the product?
Did I say coproduct?
Yeah.
Yeah, product, thank you. Product, appreciate it. So, we need the product now. So, we want any other vector space X, which maps into both S and T. Those two maps need to factor through the projection map that we will construct off of our product. So, any proposals? Okay, so no, I fucked up, guys. I did fuck up. You were right.
Sorry, what?
It is in fact both, because in vect, finite products are isomorphic to the direct sum.
Yeah.
The tensor product is this is the tensor product, which is something else from the product. It is different.
Okay.
Yes, it is in fact different. So that's really unfortunate, guys. My bad. You were correct, and I appreciate you calling me out on my bullshit.
It's
Wait,
a
wait,
product,
wait.
no product.
That is R5.
So, yeah, like these are both like these.
I saw like you mean time means like tensor product, so like I was like okay.
What?
I saw you mean times mean like tensor product.
Yeah, I meant the categorical product, which I thought was
so it's
which,
R5.
which I thought it was the same as the tensor product.
No, it's not.
Well,
No, it's not.
this is meant, like,
Fuck you.
like pertaining to your question about whether this changes for infinite, this has to do with like duals being stupid and like infinite.
It does have to do with duals being stupid in infinite space. Exactly. Yes. Precisely. Like when you have the difference is that when you have the direct sum, I think it's like finite support, and when you have the direct product, you can have arbitrary support. Like it's like there's some terrible shit that happens with the English. But anyway, this is wrong, and I'm going to move on past this example because I don't want to think about it anymore. Yeah.
So just okay, but they're both this.
Yes, they are in fact both this. Yes.
So coproducts and products are equal in the
Finite.
category of finite vector spaces, or like, you know.
Yeah.
Then it's not going to be a self-dual category, is it?
The category of finite vector spaces.
Or I guess is it
does-
isomorphic to its opposite category?
I think it probably is. I'm not sure. I haven't thought about that, but my guess is yes. The thing that the category of finite vector spaces doesn't have all products. It has all finite products. But yeah, the finite products are
The coproduct and the
Yeah.
product are the same thing, but
for finite index. Yeah. Good. Okay, so yeah, I fucked that up. Glad we've established that. Good. I'm gonna stop thinking about vector spaces now. Bro, my feet are covered in chalk dust. So my laptop, that's sad. Okay,
The math classroom makes me.
we are going to move on to another universal construction.
Let's go.
Equalizers. So, an equalizer is a pretty, like, it's kind of a lot simpler than this. It's like, we want to generalize the idea of, like, the set on which our two maps are equal. So, like, when we have set, say we have, like, R, so R, right? And we have two maps, or say like R to like R plus, R to equal, right? And we have two maps, we have the like times 1 and squared, okay? So what is the set on which these are equal? What is the set on which these are equal? Incorrect. 0 squared is also 0. So the set is 0 and 1. Good. Now, like, in particular, like, but these are just sets, and again, any, like, this is different from the set 4 or 5, right? But they are isomorphic, right? So what matters is, what matters is isomorphism, as always, right? We don't really care about the object, we care about the morphisms. Here we have the morphism, you know, it's this canonical inclusion, which, when we do this inclusion, and then we do these composites, we end up with the same morphism from here to here, right? So like, if we call these like F and G, so, and we call this the equalizer. So, like, we have, like, iota, F of iota is G of iota. This is an equalizer. So, in fact, we will define the equalizer to be the thing such that, like, you know, we have our equalizer here, and there exists a unique map here which satisfies the thing. Is this the right place? Does it live here? Does it live here?
We should call it X, right? It's not E.
Yeah, like, I'm gonna check out that. I don't want to put this up again, guys. I've had enough taste of floundering because I remember the definition wrong. Yeah, okay. So, okay. E here, like this now, such that for every other thing, X, which maps into R, I'm gonna be very careful. I really don't want to finish.
The definition we were given was that if that arrow X to R, which we call and satisfies like and equalizes F and G, then there exists a unique morphism U from X to E.
Thank you.
A unique morphism such that the diagram
Yeah. This, what did you call this one?
U.
Sure. So there exists a unique. Okay. Cool.
Such that the diagram, or the left side of the diagram.
Okay. Cool. That's the equalizer. So we've now done the 3 universal constructions. I'm not going to go into examples for this because it's pretty trivial. Like, I can't if people want me to. What's important to notice is, again, yes, the equalizer, like we have this set 0, 1, but what we really care about is the embedding into R. Okay. So these are 3 examples of a universal construction. In particular, these are limits and colimits. Okay, so this is the limit, that's a limit, this is the colimit. What does those words mean? What those words mean is something along these lines. Okay, so I have some diagram, like a limit. I have some diagram. Say like, I don't know, A and B and C and whatever, okay? Cool, so I have some diagram. And, so, like, L is a limit for this diagram. If for all other X, which have maps into all of these objects such that the things commute. L with projection is a limit. If there exists this unique morphism. So, for example, the product is the limit of the discrete category S. The limit of this diagram, with no morphisms, right? The limit of this diagram is the product. What I'm saying is, I have my limit P, such that for all other X, there's this unique morphism in, that makes it that the diagram can move. The equalizer is the limit of the diagram. This. Can you guess what a colimit is?
So the direction of the arrows.
Yes. So the colimit says, so we have a, oh, sorry, so I have this, L is the colimit of this diagram. L along with all these morphisms, all of these like quote unquote inclusions from all the ABC into L. The colimit is for all other X with inclusions. There exists a unique morphism from L to X. Yes?
Can you give me time to think?
I will consider it.
So,
Yeah.
I guess, do they have to be, does it not matter if they're like projections or inclusions, like the maps between?
Yeah, so that word, like, what does that word mean?
Yeah, I guess I'm asking if it
Yeah.
means anything.
So I've been saying projection and inclusion for like intuition reasons. No, you do not like the word projection doesn't really mean anything on its own. You can define like surjections and injections based on equalizers with the zero map if you really want, in certain ways. And with certain universal constructions. But no, really, I'm just saying that the morphisms exist and that the diagram exists. It like just so happens that you can prove that that's a like projection if your category is an appropriate notion of projection, and the word projection means something.
Okay, sure, I see.
Yeah. More questions? Okay, so coproduct is a colimit. Great. I hope I didn't flip the definition of limit to colimits. I always do that. I'm just gonna check that, because that would be embarrassing. Since you brought up earlier, like products of arbitrary like index sets, you can just have a discrete category of arbitrary, or rather a discrete diagram. Right? Like you can have, like A, B, C, D. You can make a limit to this diagram, and that's going to be a product of A, B, C, and D. And you can prove that it's isomorphic to when you do the individual pieces. Yeah. And in fact, I think it is true, if I remember correctly, that if a category has all products and equalizers, like all like infinite products and equalizers, then it has all limits, which is cool. The dual notion is true for colimits.
Or so we, yeah, sorry, no, you go.
Oh, okay, it has all limits, as in you take any collection of objects.
And there exists a limit, with all the limit morphisms, yeah. Average?
Are co-equalizers interesting?
Yes. So in vector spaces, for example, or in like abelian groups or whatever, if I have some map, so I have like V and W, I have say some map F and I have a zero map. The equalizer is the kernel. The co-equalizer is the co-kernel. As one might expect, right? That's just an example of where you might care about this. I'm sure that and lab has more examples of co-equalizers and control F for co-equalizer.
Sorry, sanity checks.
Yeah.
Which things in the category? Which things are in objects mentioned? Which ones are in the category? Which ones are in the diagram?
So you can view a diagram as a subcategory of your category. Yeah.
But like when you're picking X, is that in the diagram or is it?
No, X is in the category.
X is in the category.
Yeah.
A, B, C are specifically in the diagram.
Yeah.
L is in the.
L is also in the category. Like I start with the diagram ABC.
Yes.
The limit L, just something else in the category, satisfies this universal thing for everything else in the category.
And I assume for the class that the diagram is exactly what I expect it to be.
Yes, a diagram is exactly what you think a diagram is. I might go more into diagrams shortly, because there are ways to formalize that, obviously. Okay. Are people ready for me to move on past universal constructions? Yes? Any other questions on universal constructions? Now's a good time.
I guess we were wondering what the construction looks like if it's not too long for being to build up any what's it called, limit.
From the product?
Yeah.
I don't know off the top of my head.
Okay.
I've never needed to. Like, usually you don't bother constructing your products. Like, it was such a waste of time to sit there and go like, oh, you know, what's the order of pairs? Like a set that has A and like 1 comma A and like all this stuff, right? Like, I did that in order to point out that it's a waste of time. And that we don't actually care, we just care about the universal property. So, if you know, like, the theorem is true, that like, if you have all products and like, equalizers, then you have all limits. So if you know that this is true, then you draw your diagram and you say the limit object, and like constructing it is often not that meaningful. Like you don't really, usually you don't care about the object, right? Like I don't care about the set 0, 1, I care about the morphism out of it, right? And so it is like, you do very often care about like the behavior of your limit object. And so like, there exist very interesting examples of limit objects everywhere. Like for example, if we take, let me make sure that I do this in the right direction. So you take the Indra's mod key. There exists a map of that from Indra's mod p squared, given by, okay, there exist several. I need to make sure that I'm thinking of the correct one. I think it's just, we're just gonna mod out by like p squared. Okay. So,
Or
like,
viewing these as groups. Or
Yeah.
strings.
I'm doing these as fields actually.
As fields, okay.
Yeah. Or as groups if you want, or as rings if you want. Okay. And there exists another one. The mod. It's like, okay, this like mod p squared is just like multiply by p, basically. Is that true?
Do you want p squared? Do you want p squared?
Whatever. Mod p squared. Yes, it is valid. No. What is the? I don't
Right,
wanna-
my question was less about the objects themselves and more about the construction of, like, it feels like the product and equalizer are these sorts of like combinators you can use to, you know, if you axiomatically know that you have a product or you have all products that have all equalizers, then you can use the black box product and black box equalizer to build up any, like, you know, you give me a diagram, I give you the limit of the diagram in terms of those two things.
Yeah. It's a good question. It's something maybe we
Because is
can
that the
figure out
right way to
after,
put it?
because I am curious now, but I don't know.
Okay,
off the
yeah,
top
no
of my
worries,
head.
sorry.
Okay. Cool.
I think the progression factor is about 5, which is good, but it's not that great.
So,
For my recollection. I could actually check.
since I am writing this, I will finish what I'm writing. So, we like, we can do this, right? Multiply by p, right? This is like this is essentially the same as doing like mod p squared, right? Or like mod c cubed. Or sorry, mod p squared. Like, because when you multiply by p, you kill the top power of p. And this continues, right? E to the 4z and so on. We have this like this infinite diagram here of like projections down onto smaller. The limit of this whole thing is the p-adic numbers. So like if you write this as like integers written in base p with 1 digit, and then with 2 digits, 3 digits, so on. This is just like infinite. Like these kinds of constructions are like very nice. And like you learn about the p-adics by projecting down into just a smaller powers of p and seeing how those things behave. And like, so this is nice. Like, this is why we care about this. Cool. Ready for me to continue? Oh, my, forgot that out. Plug my things back in. Page. Thank you. Please don't be embarrassing. Don't be embarrassing. Don't be embarrassing. No, it's not. Okay. Cool. So. Great. Back to our presentation, guys. We've now finished like the first 2 slides. Okay. Functors. We've talked about categories, and we have morphisms in our categories. Now we want to map between categories. Right? This is the thing that we care about doing very often. For example, like sets are very easy to think about. So sometimes we like to think about sets of things, like topological spaces. Maybe we care about the set of points in the topological space, so we can point at a point and say, hey, that's a point, right? Things like this. So, functor map all objects to objects and morphisms to morphisms in a way that is compatible with all of the like things that you care about. So, in particular, the identities get mapped to identities, and compositions get mapped to compositions. I'm using like maps to arrows here because these are not morphisms. Right? All the stuff up here is in the category C. All the stuff down here is in the category D. Sense? So, examples. There are 4 functors from that category to that category. Do you see why there are 4? Wait for the first person to tell me why there's 4. I like how you both did this at the exact same time.
Oh, you have 2 choices for the object map and 2 choices for the morphism map.
Incorrect.
No?
So, like, if you try to do this, if you try to map like A to E, B to E, and this morphism to this morphism, that doesn't work.
Okay, I mean, there's 2 choices. Like, you can map A to E and B to V, or you can map A to V and B. Oh,
No, you can't.
never mind. Yeah, you can't do that.
There are 4 apples in the right diagram.
Hmm?
There are 4 apples in the right diagram.
Exactly. They're identity arrows on the ND.
Oh.
Yep. So this arrow can map identity on E, which maps A to E and B to E, or we can map this arrow, or to the identity on D, which maps A to B and B to B. Sense? Great. Whenever a category D looks like C with more structure, we can define a forgetful functor from D to C, which forgets that extra structure. For example, group to set. We forget that it's a group. So the group poems become just set maps between the elements of the set. Oh, did I start the recording backwards, or did I just clear my? Great, okay. Yeah, and that makes sense, yes? Okay. Top to set takes continuous maps to the point set map, where here this particular forgetful function just forgets that's the topological space. So we have the points of the space. Make sense? Lots of other ones. We can take like a group to abelian group. We take abelian group to group, right? Which just forgets it's abelian. It doesn't really do anything. So on. A question on that before I continue? Okay. The free group functor from set to group takes a set and it gives you the free group. Does anyone, please raise your hand if you know what a free group is. Okay, not everybody. So the free group on a set is, that's fine. A free group on a set, so if I have some, I'm going to erase all this shit. So the free group on a set, if I have some set like A, B, this is my set, okay? So the free group, let's call this X. The free group on X is like, I have things like, there's an identity because it's a group. I have like A, and I have B, I have A inverse, B inverse, I have like A, B, A inverse, etc., right? A, B squared, A, B, A inverse. Like, now, this is just equal to like A, B squared, A, B, yes? Like, the reduced words part here means that we reduce the things that the group, like, the group operation of like inverse has some axioms and all that stuff. Make sense? Okay. It's called the free group because it's the most free thing you can do with this guy. There's no relations between A and B. There's nothing about the commuting, nothing about anything. Question on that before I leave? Okay. The set of categories is a category. It's called a cat. The objects are categories. The morphisms are functors. Functor composition is associative. This is a true statement. So, yes, now, before I talk about the product of categories, if like that construction that I gave satisfies a universal property, where now the morphisms are functors between categories. This is a like common trick in category theory is to go one level up, right? Like we have like this. Let me erase this shit. So we have some like category which has like stuff in it, right? Like it has like A or B, right? And we have a different category D which has other stuff in it, like E or V, right? And we have this like functor between them, okay? Now just like hide the inside of this. This is an object called C, this is an object called D, this is the morphism between them. Right? So we can do that. And then we can talk about like other categories X, and we can talk about like maps onto each of these. And then we can talk about like this category and functors of each of these and how there exists a like unique functor from X, right? Like this is the same construction as before. The definition I gave you for the product category satisfies all of these conditions. Just like the set definition I gave you satisfies these conditions. Make sense?
So like the definition is kind of recursive, to be honest.
Yes, it's quite fun. Category 3, like to do that. Okay, now for one of my favorite examples of a functor. So any group G can be viewed as a category, VG. The category has one object, we'll call it star, just for funsies. And the homomorphisms of the group are the morphisms, are the elements of the group. And our group composition is group multiplication. We have associativity because group laws, right? We also happen to, it is the case that every morphism is invertible because it's a group. So this is the groupoid. Remember before I said what a groupoid was? The category of all morphisms are invertible. This is why that's the case. So a group is just a groupoid with one object. Okay. So, because groups G and H, the group homomorphism is a functor from VG to VH. It takes elements to elements in a way that's compatible with multiplication. It takes morphisms to morphisms in a way that's compatible with composition. Huh? Who here knows what a G set is? This is like a set with a group action. Hands up if you know what this is. Okay, so I'll just say this for you. But you know, I'll define what a G set is briefly. So a G set is like, I want my group to act on a set in some way. So like, for example, like I can have the like symmetric group on 3 elements, right? Like I can say I have like S3, right? This is a thing that permutes stuff, right? Okay, and I can say that this acts on the set like A, B, C by the by permuting shit, right? The important bit is like this effectively, so every group element becomes a endomorphism of a set, right? A morphism from the set to itself. So it like takes, like, for example, like the permutation 1, 2 might take A to B and B to A. So it's a function from A to C to A to C, where f of A is B, f of B is A, and f of C is C. And this has to be compatible with the group operations. I can also have like S3 act on this like triangle. And how to do that? Whereby like it's probably like the set of points in the triangle. And how to do that? Well, like I can like label the like vertices 1, 2, 3, right? And I can say that like the like 1, 2 mirrors it along this. So a functor from BG to set is what? Object to object and morphisms to morphisms. So it takes this object star to some object in set. So it defines a set, and then it takes morphisms to morphisms. So it takes the group elements and it turns it into endomorphisms of the set in a way that's compatible with the composition in the group, i.e. compatible with the group operation. That's a G set. Questions on that? Okay. No questions? No questions. A functor from BG to vect is a G representation. Hands up if you know what a group representation is. Okay, more of you. For those of you who don't know, it's the same thing, except instead of it acting on a set, it acts on a vector space. So every element of the group, like I can view this as like living in like R squared, right? Like R squared, and I can say that like 1, 2 is the matrix that mirrors, right here. So again, I get a vector space, and I get for every group element a endomorphism of the vector space, which is compatible with group operation. This is a representation of your vector space. Like when you, those of you who have learned about like G sets and G representations before, know the definitions are like often kind of opaque, right? It's like you need like a morphism into like GLN or whatever, and like it needs to be compatible with all the shit and blah blah blah. And like G set is like kind of similar, but the morphisms is into like the symmetric group, but actually like I said the morphisms into GLN and the symmetric group, you have to prove that. That's like not a thing you start with. That's not the definition. You have to like, you say that it like there's a map into like things, and then you have to prove that it's sufficient and blah, blah, blah. It all just functors into the category in question. Right?
Simon TJ, you mentioned homomorphisms are functors that goes both ways, right?
Yes, it should. I think so.
Feels like it does.
Yeah. Yes, it does. Okay. Last one. B is a function from group to cat. It's called the de-looping. It takes a group, gives you a category. So when I say you can view a group as a category, literally you have a function that does that. It takes the group and gives you the category. Right? Make sense?
Wait, all three of these are
All three is there what?
equivalences?
These three are equivalent with yes. Yes. So,
What do we mean by equivalence?
And as in like a GZ also
is
is
a
a functor.
function. Like, these are one-to-one.
Oh, yeah.
Yeah.
Wait,
All functors of a G set are G sets, all G sets are functors of a G.
oh, yeah, yeah.
These notions are equivalent.
Why do we use the word view? What's that mean?
It's super fun. It's a really fun question. So, you know how before I said you have the fundamental groupoid of a space? Okay. So if we have pointed topological spaces, so this is,
void.
yeah, so the fundamental groupoid is when we have paths of the homogeneity.
Oh, right.
If we have a pointed topological space, so the category, okay, so we have the category, like, I'm gonna erase all this shit. So we have the category top, right? Top has topological spaces as the, as its, objects. And it has continuous maps between them as it exists. The different category called top star is the category of pointed topological spaces. So it's a topological space with a special point labeled on it. Okay? And the morphisms in top star are continuous maps which send the point to the point. Right? So there's a point in the input, the point in the output, that point needs to go to the point. Right? So like we can have the like unit interval like from like 0 to 1, this is our point, okay, and we can have some like topological space n, and this is our point. Now that we have this, we can consider the category of paths. Okay, so
Is this related to the notion of rel?
what?
This is related to the notion of rel,
What is well?
like in homophobia theory, when you said like leave a certain set of like leave the boundary.
Yes, I think so. I'm not super familiar with the terminology, but I would guess so, yes. So we can think of like homomorphisms from here to here, right? So these are things that look like that. But it's like, it's kind of like that. Instead, let's consider a circle with a special point. Now our columns look like this. Now I'm gonna say, I'm gonna take a different category. I'm gonna say, like, I don't remember the actual notation for this, so I'm just gonna put a tilde over it. Okay. So this is gonna be my my morphisms will now be up to homophobia. Okay. So now like this is the same as like this, right? Okay.
Was just fundamental.
Yes, so now what we have is the, like, I can consider the category where my objects are these, wait, shit, one sec. No, I can consider, sorry. I can consider the one object category, where my one object is the space. Yeah, where my one object is the space, and my morphisms are like paths. Is that? I don't know.
Or I guess we just say the object is some abstract object, and then the morphisms are these homomorphisms, or like homotopy classes of homomorphisms,
Yes.
and then
And
our
the composition
is
is
just concatenation.
concatenation
Yeah.
of homotopy. And now I have a one object category, which is the fundamental group.
Yeah, it's just like be a fundamental group of
Yes,
topological
exactly.
space. Yeah.
This is like the looping of the space. I got the loops out of the space.
Oh.
Then I deloop it.
You deloop it. Delooping sends that category to just like the fundamental group.
Wait, fuck. Did I flip it around?
Oh, sorry, it goes in the other direction.
Ah, man. I think I flipped it around.
Oh, so I guess you're like taking all the loops and then you're like saying, oh, what is the group?
Okay, so I think in the category that we're thinking about, oh yes. So the looping of this like category, it creates the group out of it. I'm like somewhat not super great on this.
No worries.
But this is the general idea. Is like, it's about taking these loop spaces, and like when you look at the fundamental like when you look at the fundamental group as like a category, like visually look at it, like it looks like your space kind of. Like once you mod out by the composition. Like, everything that I'm saying is super vague, and that's because I don't understand it very well. So I'm gonna move on past this, and I'm gonna go on back to the implementation. But the general idea is that it's related to the fundamental group work. And that's why I call it looping. Make sense?
I assume we can do something similar with what's it called, posits.
Say that again?
We can do something similar with posits, right? We have another function from
Oh,
posit to
yeah,
catch,
absolutely.
Yeah.
Yes, that's good. I don't think it's called looping though. So do I want to give an example of something that's not a functor? Sure, I will. So here's something like reasonable looking that's not a functor. My reasonable looking thing is I have this like functor like f from like vect to like I guess vect, which takes like w and it like maps it to like it takes like w to k to the w vect. I should have been writing like vect this entire time. K is the field. So like k w to the k to the w, which like
It maps W, the object W to the object. Oh.
yeah, it like maps w to like the like list of its components. And this is like not a functor because this requires choosing a basis.
And it has to be finite dimension.
Sure. Call it finite dimensional. Like
Or I guess it doesn't have to.
this is still not a functor. This requires choosing a basis, and choosing a basis is not necessarily compatible with all the morphisms. Generally, most constructions of functors, like, it's pretty easy to tell whether or not something is a functor. If you didn't need to make any choices when you chose it, it's a functor. If you had to make a choice, it's not a functor. The axiom of choice breaks your functors. Don't use the axiom of choice. Like, yeah, you can choose a vector space, but like, it's like it's not necessarily true that like if I then consider like V, which is like the same as W, but I choose a different basis in it, and I do the identity morphism, now I'm like it's not the identity on the output, right? Like this is fucked. So yeah, I just this is just fucked. That's an example of something that's not a function. And like you can alleviate this by like actually including the basis information in your category. So you can have the category of vector spaces with basis. This is the same idea that we had to do here for top star. Like, I can't just pick a point in my topological space. I have to include the point in the object definition. Make sense?
Could we keep the formal definition of function again? And just like see like which axiom is being violated?
It's the compatibility with completion.
Oh, great.
And like identities to identities. Make sense? Questions on functors before I move on? Okay. Natural transformation. So we have so far. We have so far talked about categories. The categories have objects, and then they have maps between the objects. They're called morphisms. Now we talked about categories. They have functors between the categories. We have our category of categories, where the morphisms are functors. Now we want maps between functors. Okay? Because this is category. You always want to be able to go one level up. Right? Let me make sure my thing is still running. Great. So to do so, we will describe natural transformation. So, given two functors, f and g, with the same domain and codomain, a natural transformation from f to g has. Now, this definition is a bit convoluted, and I'm going to aim to make it less convoluted. For every object x in our category C, a map between the output of f and the output of g. So this map is a morphism in D, right? Such that this square, this naturality square, commutes. Right? Because these are all morphisms in D. So we got f of m and g of m by applying our functor f or g. This eta is our natural transformation, which takes us from the outputs of f to the outputs of g. And we want this square to commute. I've drawn this double arrow because it's dangerous to draw this double arrow. The double arrow doesn't mean anything. Okay? There is no action on morphisms. The natural transformation doesn't do anything to morphisms. F of m is just the output of m and f. G of m is just the output of g, of m and g, right? Like, they already correspond to each other immediately. There is no notion of a morphism between morphisms in most categories, right? Like, the natural transformation just maps the object in a way that's compatible with these like already pre-existing like morphism correspondences. Now, this is the first time today where if it doesn't make sense, it's like somewhat expected, because this is confusing. Examples for this one help a lot. Before we you should feel free to ask questions right now.
Examples will or will not?
Examples will help.
Will, okay, good.
Did I say will not? Did I say will not?
I didn't hear you properly.
Okay.
That's why I clarified.
So I drew it like this over there. Why does my laptop keep? Dude, you're plugged. Not plugged in. I keep stepping on the cable. Okay. So I drew it like that over there. I'm going to draw it differently on the board. So the way that I will do this generally.
Is it appropriate to think about this by analogy with chromatography?
Yes, but I'm not going to explore that today.
Yeah, I'm not saying you should. I'm just asking is that
Yes.
reasonable?
Yes, it is a very reasonable way to think about it. So, But like it's like not in the way that you might expect, because usually like a homotopy, like the endpoints are fixed, and like you're deciding how to map the path. Here the path is already mapped. You're deciding how to map the endpoints. Like it is more subtle than it might be immediately like obvious. Like if alternatively you view these as the endpoints and this as the path, then okay. But like now things are getting confusing, right?
Or I guess like if we look at the category from the, sorry, this is getting too deep into the weeds, but we can assign each topological space to a category, right? And then we can put paths as, as the paths as morphisms and the points as objects, then would an actual transformation in the category of those categories be homotopy?
Natural transformations don't live in a category. They live between functors.
Yeah, but the functors would be, what would the functors be? We could forget it, sorry.
Okay. I'm interested in exploring your question after class. Okay. So, I'll write this differently. We're going to consider C land and D land separately, okay? So, we have our little things, we have our like A, maps, B. Nice. So, I'm going to block this up. This is what happens in C. I'm going to blow this up into a naturality square. That's what it's called, a naturality square. Okay? So, I'm going to have, now we're going to be in D land. F land is the subset of D land, okay? F land here refers to the apples of F. So, F stuff will be up here. So we're going to have F of A. Bro. F of A maps to F of B via F of M. That's just what a functor does. It takes us from C to D. G of A maps to G of B via G of M. And our natural transformation has components for A and B. They're called components. Eta A and eta B. That's that this whole thing. Okay? This is like not materially different from that. I just wanted to establish that I'm going to draw it. Oh, and like, notably, like, this diagram commutes means that. Right? This is a morphism, this is a morphism. So, for example, GLN is a functor from ring to group. Or field to group, if you like. It takes a ring and gives you the group of n by n matrices with entries in that ring. Sorry. Totally is field to group, right? Whatever. Where I'm.
Can we talk about matrices on what then?
Is GLN a ring? Sorry. Whatever. Okay, I'm just gonna say field to group. So it's a functor from field to group. As is this, which is the set of units fundamental location. Okay, so like we throw out 0. Okay. Determinant is a natural transformation from GLN to multiplicative group. What does this mean? You think about individual components. Imagine plugging in R, okay? GLN R. And this is like R cross. Determinant is a morphism in group from GLNR to R cross. That's correct, right? That's what it does. It takes, it's a group homomorphism, which takes a matrix and gives you the determinant, which is just a number. in our class. Yes? Yes, no? Huh? And yeah, ring is fine. Ring is good because GLM by definition is going to be invertible ones.
Wait, sanity check, what's your second function again?
This takes like it takes like R to like R minus 0. It takes Z to 1. It takes like Z adjoint 1/2 to a set of like powers of 2 or 1/2. Sorry, this should be 1 minus 1. It's invertible elements. Like it's the multiplicative group associated with it.
Okay.
Make sense? Okay. Or minus 1. Cool. Does that make sense? Yes, maybe. In this sense, the natural transformation is sort of, from this perspective, it's a way of packaging up a bunch of morphisms that are parameterized by stuff in a different category. So like, this is like parameterized by rings. Like if I fix a ring, there's just a group homomorphism from GLN of, I don't know, V adjoint X to like V adjoint X cross. Right? That just exists. It's called a determinant, right? That's what the determinant does. You like do the rule. You write down like AD minus BC or whatever, right? And like that's just fine. The naturality says that when I move between these, things are compatible. And that's like a lot more sophisticated, and I'll get more into it later. But to start, you can say like a necessary like piece of being a natural transformation is that I sort of have these morphisms that are parameterized by the elements in the other category. These are the different components of the natural transformation. Does that make sense? Questions on this example before I continue? Or more examples only? Okay. So, obviously, we want to make a category out of our functors, right? So we do that. Now that we have the idea of morphisms between functors, we can define the functor category. So if I have C and D, in the category of functors, the morphisms are natural transformations. These are really ubiquitous. These are like super ubiquitous. For example, given a group G, the functor category, a functor from Bg to xk, is the category of k-linear G representations. And please have it. Some of you don't know rep theory because this is usually a kicker of an example, because think about the definition of intertwiner. Okay, raise your hand if you know what an intertwiner is. Okay, one hand. Oh, well, you've taken a class where you should have
I took like halfway. I got like halfway through that class, so
Okay.
it was kind of dying.
Okay, so all the time what an intertwiner is. It's one sort of intertwiner. So an intertwiner. So we have two group representations. We have, so let's say that I have some group G. We can stick with, did I erase it? I did, okay. So we have like S3 acting on R squared by like this triangle action, right? So let's like call this like rho, okay? This is, okay, so let's call it rho, okay? So rho is a group representation, right? It takes a element of S3 and it gives me a morphism in, it gives me a endomorphism of R2, right? Okay. also have S3 act on R cubed by like basic permutation. Okay, so I have 3 basis elements, I just permute them. Okay. Let's call this, what's the other letter besides rho? Sigma. Thank you. This is sigma. Okay. So a intertwiner is a morphism of representation. Okay. What is an intertwiner? An intertwiner between rho and sigma is a matrix U from, let's call this like V2 and call this V3. Okay. From V2 to V3. Such that it's like U times rho, like all G. U times rho of G is sigma of G. Right, that's how that works? Yeah. So basically it takes me from one representation to the other. So it I think that this is the definition. I'd like things corrected. Yes? Someone who knows different minor? I'll look at it. It doesn't tell me I'm wrong. So the idea is I can either act on this vector space with S3 and then go there, or I can go there and act there with sorry. I can either like start here, act on it with S3 and go there, or I can start here, go there, and then act on it with S3, and these are the same. That is an intertwiner. Okay? It's a map between representations. This is exactly that. In this case, we have one object. Yes? Do we? Is that true? Wait, can intertwiners exist between representations of different vectors? Sorry,
Yeah.
what?
Yeah, sure.
Yeah, they can.
Like your things are matrices.
Yeah, so are they gonna be not square? Is that okay? Is that legal?
You fixed K though, in the definition.
Yeah, but I don't think that.
Or you're saying it's not necessary?
Like regardless, you end up with a thing of the same dimension as your intertwiner, right? Like what?
Okay, so you're saying that the intertwiner should be square, that I should have both of this dimension. No?
Like this is fine.
There's
right?
no like restriction on dimensions.
Okay.
Yeah.
So why are eta A and eta B the same here though? Like what is, in this case, I have my, okay. Oh, it's because like A and B are both star. Like, this is a morphism out of VG. Sorry, this is a functor out of VG. So there's just one object in VG. It's just star. That's a U. Because like A to A it's a morphism in vect, right? Parameterized by star, but there's just one star. So there's a map between these two vector spaces that's compatible with this, where this like G is sigma and F is rho. So these are both representations of G, which is a functor from VG to vect. like, this is probably not super compelling of an example if you haven't seen, like, in intertwiners before, but like, generally, like, the definition of intertwiners is like quite opaque. And like, this tells you that it's the only thing you could possibly do. Like, it is the natural definition because natural transformations, right? Like, there's nothing else you can do. And like, there's also an equivalent thing for like intertwiners for G sets, and it's again, it's just morphisms in that category. You have no choice in the matter. Okay, questions on this before I move on? Okay. Oh yeah.
This is a question that probably doesn't have an answer, but
Well,
we probably don't have any simpler, non-trivial examples of categories, right? So we can see like what's so natural about the definition of the natural transformation.
Yeah. Let's see. Well, what's a fun little?
But don't worry, there's not. I guess the group actions and representations are the main place where
Yeah.
it is in an underrepresented.
Oh, do you have, yeah. Let me just see if there's any like last example on yeah. Oh, let me, how do you do this with natural transformation? I said earlier I would tell you more about diagrams. A diagram in a category is just a functor from the diagram category to the category. So like we can consider like this diagram. You know, we've had this before. It's like times one, so like squared r. Okay. Like we have this category like this is the category. And then we have a functor from this into like let's like call this category D. This is D.
So every diagram can be called a category.
Yeah. This is
Just the
a
category that you're drawing.
like any diagram where I haven't actually written what the things in the diagram are, right? Like this is a diagram for one phone. This is a diagram in a category, right? To get here, I had to like actually define a specific functor from.
Are we saying there's a diagram that's representing something inside the category, or are we saying that we're like formalizing the idea of a diagram as a mathematical object and then saying that this forms a category?
Sorry, can you say that again? I'm not sure I understood.
Are we saying that these are diagrams that are depicting objects and morphisms within the category that is already defined, or are we formalizing mathematically some notion of a diagram as a construction and then saying, hey, this forms a category?
Something between these. I'm saying like our intuition from like before I was saying diagram to mean two things. I was saying either to mean just like a like abstract diagram like X or Y, or to mean a like particular instance of a diagram, right? And like I'm giving that meaning now. I'm saying the like abstract diagram is a category in and of itself. Like any particular diagram is just a category, right? Like I just define this category D, which has two objects and two non-identical, right? And then the to make an instance of this diagram in field, I have to just like define a function from that diagram. That make sense?
Yeah.
Questions? Okay. So, I'm gonna unplug again. Okay, so what I said, well, I can do something with function categories about that?
We're talking about natural transformations.
Yeah. I don't know, I feel like these are like these are my like default like simple non-trivial example because like I'm very familiar with group reps and most people who I teach this to are. Like this this PowerPoint was originally for my like algebra seminar, right? So like all the people there had just taken an entire course on group reps. So like the book was replication theory, right? So like I also think whatever. So I will start a ChatGPT.
Hey, it's fine, we should do this later.
Yeah, well, it's like important that pedagogic. Okay, so we will proceed. For now. That's the end of my natural transformation shit, seriously. So I have more examples in mind. I feel like I want to give you more examples. Nope. That's all the examples I have in here. Crying. Can I announce that? So okay, here we can. Oh,
Sorry. Every subject dominant. We've got this classroom from 6 to 10. Do you think? Sorry.
yeah, it's all good. We'll get out of here.
Okay. No worries. Do you mind if I just have a bunch of music stuff here? I'm just gonna put it there, but
That's
you keep
totally
going.
fine. Yeah, we'll be out within 5 minutes or so.
Okay. Yeah. I mean, even until like 6:15 is fine.
Oh, awesome! Thank you. Hell yeah, that's a big improvement. Okay. So great. I have an example of the function category for you. Simpler. Take the ChatGPT. So,
Or you can teach.
What?
Or you can teach.
Yeah.
Natasha and Pierre, degree comments from meeting points.
Have an orchestra rehearsal, so there's going to be a lot of instruments soon.
Good luck.
okay. So, cool. Let's do an example. Let's make a little category. I'm going to call the category 2. I'm going to give you a underline. Okay? So 2 is this category. Okay? This is the category 2. So consider the category. So let's consider the functor category. And pick your favorite category to go over here. Your favorite category? Group? I like that one. Okay, so what are the objects here? The objects here are functors from this to group, which we've established is just an arrow in group, right? Yeah. Because deciding where the arrow goes tells you where A and B have to go. You have one choice, which is which arrow does this hit. So let's call this NCF. Okay. So like NCF0 is arrows, so it's group points. Group points. Right? What are the morphisms here? These natural transformations. Right? Okay. So what are those? Natural transformation is, we need, so a natural transformation needs an A to B and an A to A and an A to B, which are both, they are arrows in group, right? Okay. Like, so like, call it X is in group 1 from like, okay. So I need 2 functions, right? Let's call them F and G, right? Bro, F is F and G is G. Any better name for the function? Any suggestions? Any suggestions?
P and Q, I don't know, man.
Okay, P and Q are our functions now. Thank you. So, P and Q are from 2 to 3. And so, eta from P to Q has like eta A from P of A to Q of A. And it has eta B from P of B to Q of B. Such that for all morphisms, for all say phi, okay, for all phi, we need to be the case that eta, wait, is this morphisms? Oh, in the input category. So it's literally just this guy, right? Let's call this guy M. Okay? But that, we don't even need to do overall, because it's just one, right? Such that, please come back. Such that, we need, P, so we need like,
So we can view the elements like curly F as groupable morphisms, right?
yes.
Yeah.
That A to B of P of M is equal to A to B, P of M is equal to Q of M, sorry, A to A. Yes? I think that's correct. Yeah, you do A to A, and then you go along Q. Yeah, because eta takes you from P to Q. Good. Okay. So what does this mean in practice? So M is just this arrow here. P of M is a group home. Q of M is a different group home. Right? Let's call them phi and psi. Okay? These are two group homes. This eta here is a map in group. So it's also a group home, right? So a natural transformation from P to Q is a morphism, like is a pair of morphisms here, such that precomposing with this, like this composed with phi, is composed with Q. So honestly, I think you have one choice here, which is phi over here and phi over here. Right? So like kind of a trivial example, right? But this is okay. So there's literally only one natural transformation between any pair of No, that's not necessarily true. You can have other group homes that work here. Like this one exists, but there are totally other ones, right? Like for example, if P and Q are both the identity, then like if P is the
Those just have to be inverses of each other.
no,
No, they just have to be the same.
not even, yeah, but like, yeah, these just have to be the same in that case. But like, these can have different, okay, this can be, say, from like I need more letters, say like alpha to beta, these are groups, okay? And this can be from like gamma to delta, right? Then this needs to be a transformation from alpha to gamma, and this needs to be something from beta to delta that makes these work out, right? So you can even put C here and C here. Like this is more sophisticated and complicated than that, right? I don't have much more to say about that. This is an example that I just pulled out of the hat, right?
It's a pair of groupable morphisms which have this equation.
Yes. Like the goal here is to find a way to turn this group of homomorphism into this group of homomorphism, or rather, turn this one into this one, right? Like, in some very vague sense. And the way you do that is by sort of connecting them up, using a alpha to delta translation here and a beta to delta translation.
I guess without representation theory background, it's kind of hard to see why this equation is, or why it matters. Why it should care about
It's
it.
honestly kind of hard for me to see too in this example. I'm sorry that I don't have a better
Yeah.
example for you. So there are a few directions that we can go from here. We can stop. If it's fixed. We can talk about adjoint functors, which I think is maybe fucked if you don't have. I mean, no, we can really talk about adjoint functors. Or we can talk about the unit lemma, which requires understanding natural transformations. Which it seems like we kind of don't, because I don't have good enough data for this. I don't know these guys. It's to be clear. Natural transformations are fucking hard. Most of my 5 hours were spent trying to understand natural transformations. Because the unit lemma is trivial. It is just you need to understand natural transformations. So that took me 5 hours. So I can tell you the unit perspective. I can tell you about adjoint functors, or we can call it a day. Opinions. Okay, hands up for call it a day. You want to call it a day.
Yeah.
You can leave regardless of what I decide to do. I'm you're not obligated to stay here. Hands up for Ganetta.
Let's do it.
Okay.
We're seeing 15 minutes.
Hands up for adjoint. Okay. We're gonna attempt the Ganetta lemma, guys.
Yeah.
The Ganetta lemma is many things. There are many things that one might call the Ganetta lemma. They are largely all the same things from different perspectives, as is usually the case for category theory. Some of them are less powerful than others. I think the thing I learned most about the Ganetta lemma is the Ganetta perspective. And I think that's what I'm going to try to convey here. I will use a definition of the Ganetta lemma in my doing so. So, to talk about the Ganetta lemma, I must talk about the Hom functor. Okay, so there is this functor called Hom. It's C. Okay, it is a functor on C op times C, which is set. Why is this true? It's true because my definition of a category had that for every pair of objects, I have a set of morphisms between them. But these morphisms need to be compatible in composition and stuff, right? So now, why is one of these C op and one of these C? Well, we can do this by thinking about it. So let me do that. So, this guy, this takes the pair x comma y to Hom y, as you might expect. And it gives you the Hom set. And since it's on this product of categories, it needs to do something with morphisms. So it's going to take F comma G, right, to this function in to the function in Hom set of pom, pom, wait, did I say x, y, w? Did I fuck up? I think I, sorry, one second. X to z. Okay, I'm gonna write this down and then if it's wrong, I'll fix it after. X, Y, taking C to okay, let's think about this. Okay? So F lives in okay, so first off, this C is a function in pom xy. Okay? This is in pom xy. Okay? This guy I claim is in pom vw. Why is that true? Well, okay, so we started f is a function from x to z, and g is a function from y to w. Except that, like, f lives in C off, right? This is in C off. So actually, f is a function from z to x in C. F goes from x to z in C off. It goes from z to x in C, right? So in C, this goes from z to x, x to y, y to w. Make sense? Okay. So we can fix part of this. We can just plug something in on one of the sides. And plug in to get something like to get a more normal looking home function. So we're gonna have like home C of A. Okay. So this is a function which takes some thing in our category and it gives us something in set. That's it, and it literally gives us the home set, right? From A to B. And it's from C because I can give it a function and then it'll give me the, like a function from B to C, and then it'll give me a map from the home set AB to home set AC given by post-composition with my function. And also, plug in the other side. And this is now a function in C off. This is sometimes called the pre-sheaf associated with A. If you hear those words in the future, you now know what they mean. I was laughing because Al has heard those words, and now I don't know what they mean. So, erase it all. Okay. The Unetta. I'll do one version of the Unetta, and then I'll mention the others and what they mean. Unetta. Given object A in a category and a functor f from the category set, But before I proceed, why might we want such a functor? Well, we like talking about the elements of something, right? Like the points in a topological space, for example, right? So nothing about the category of topological space includes points in it, right? It's just the space exists. It's a magical thing. We would like to be able to talk about the points in the space. In some sense, like, this is the only way that we can like extract information in like a classic sense, like set theoretically, from our like objects. Is turn them into sets and then look at the elements in a set. And group elements, right? Okay. Given these, set of natural transformations, the set of natural transformations, which I'm going to write more clearly as the Hom and the functor category, just so that we're clear about our typing. From the Hom functor to f. Like, this is a functor to set, this is a functor to set. You can think about natural transformations between them. As a set is isomorphic to f of a.
Meaning it has the same number of elements.
Yes. So, and, okay, I agree with you about that. But like, it's not just that it has the same number of elements. I have a map between them. Okay. There exists a map between them.
Bijection.
Yes. Like, which, and like, I'll write down the bijection. So I'm given a natural transformation and I want to get something in f of it, right? How does this work? Well, this direction, relatively straightforward to state. So I have my A component, which means I plugged in A here, and I plugged in A here. So I now have a set function from Hom AA to f of A. And I plug in identity A. This therefore gives me an element in f of A. That make sense? Okay, I'll write it more explicitly. So, like, A to A is a set function from Hom A to Hom C A to F A. That's just what the components of a natural transformation are, right? They're morphisms in your thing, where you plugged in. Okay. So we just plug in the identity on A, which is in here. This is an element of this set. We plug it into that set function, then we get an element of this set. Okay. This is how we get that element. Okay. What the statement is saying is that that element contains all of the information about the entire Hom functor of A. Like, and vice versa. The Hom functor of A, just the morphisms out of A, the information about the morphisms out of A, contains all the information you could possibly hope to extract out of A by putting it into this thing. So, how do we go the other way? The other way is also relatively straightforward. So given, like this is the language, okay? So given A in F A, right? So now we want to find a natural transformation from this to this, right? Okay, so we want a set function a to b from hom a b to f a, right? Okay, so it needs to take a phi and it needs to give you something in f of a. Here's what I'll do. I'll take a phi, right? I'm going to feed it into f, right? Because f is a function on c. So we can take homs and turn them into homs instead. This is now a set hom from f of a to f of b. Plug it in. Sorry, this should be over. That's it. You've done it. You've defined the thing. The hard part is seeing why they want to get our equivalent. I'm going to ask them if they want us to. Yeah, we can wrap that up. You can also start coming in while we're wrapping up. That would be, yeah. Okay. So I will give the proof without giving too much of the intuition because I don't have time to do that. Whoa. Okay. So it should be relatively clear to see that if we have our element A and we build the natural transformation and then we try to get an element out of it, we'll get back A. Like we'll get back the image that we started. The hard part is seeing that we don't lose any information when we turn the natural transformation into A. So the question is, if I've defined A like this, if I've defined A like this, right? And so I'll call this like A to A. Okay? So if I've defined A like this in terms of some original eta, I'll call it eta, it's my original, okay? So if I've defined A in terms of eta half, can I recover all of eta half? Let's try. We want to know what eta hat does to some, like, or we want to know that eta half. So we'll take the one eta A okay. So what does eta A do to some hom AB, and we know this goes down to f of right? And we want to see what this would do with eta. Okay. So, how do we method this? The answer is we can take this hom that we want to send here, because this is going to be a. So there's some like C in here, which we want to send to some thing in. We take this phi, and we're going to write down here. Here's the A to B. And then once I've written this here in my input category, right? This is in C. I can now blow it up. Goodbye. I can now blow it up into a naturality square. This entire thing. So this now becomes hom AA. Now, I could have used any like random morphism here, psi. And then I would have, up here, I would have like hom of A psi, which is just like psi composed, right? And it's like F rho. Right? But I'm choosing the phi that I want to find out what happens. So, because I've done that, I made that choice. So to see where phi goes here, we can see where this goes, which means we can see where it goes down here. Which means we see where this takes the identity of A. And then you apply F to phi, which is exactly our definition of A to B A. That's all. It just does it. So the moral of the story for the meta is that an object is completely determined by its morphisms. Morphisms. In particular, the consequence of your meta is that mat of form rank A with form rank B. Assuming I haven't flipped it, is isomorphic to like form AB. So two objects are isomorphic if and only if they're representing functors are. The end.